Good morning, students. In previous lecture, we have discussed about reflection coefficient at the receiving end at distance z is equal to L. Now today we will continue that topic and we will discuss about the reflection coefficient at any distance that is L dash from the load side. Now we are considering the distance L dash. At this point we will try to find the reflection coefficient. So for that purpose, if we are considering the length from load side as L dash, then this length will be L minus L dash, this length. And we can write the wave equation: forward traveling wave plus reverse traveling wave. As the distance is L minus L dash from here, so we will modify this according to the position where we want to find the E minus gamma L minus L dash plus E gamma L minus L dash. And if we want to find the reflection coefficient at distance L dash, means here, because this is considered from load side. In previous case, we have considered here as load, that is at L. Now we are considering at any point between the line. So that is at this instant it is at L dash. So it will be reverse traveling divided by forward traveling. So that is V naught minus, we can write this e to the power gamma L, and if we simplify then we can say L dash with minus sign. Just I am simplifying this, divided by positive e to the power minus gamma L and e to the power minus minus plus gamma L dash. Now if we will further simplify, then we can find positive, here it will be e to the power 2 gamma L multiplied with e to the power minus 2 gamma L dash. And what is this? This is reflection coefficient at load, at the end of the line. So we can write it reflection coefficient at the load. So we can say reflection coefficient L at distance L dash can be written as at load side multiplied with e to the power minus 2 gamma L dash, because this is known to us, that is equal to this. And gamma can be written as load, and gamma can be written as e to the power minus 2 alpha plus j beta L dash. As it is usual, we will talk about the lossless transmission line. In that case, alpha will be 0 and the remaining term will be gamma load e to the power minus 2 j beta L dash. This is the reflection coefficient at any length L dash from the load side. In this way, if we know the reflection coefficient at length of the line, Then we can find the reflection coefficient at any particular point in the line by knowing the beta phase constant. So let us take an example, that is, there is a line of length lambda by 4 and the load impedance is 100 ohm real load is there, and the characteristics impedance is 50 ohm. Then we have to find the reflection coefficient at this point. So if we wish to find the reflection coefficient here at distance lambda by 4 from the load side, then it is required to find, regarding this we have to find at the load first, then we'll multiply from this. So first of all, let us find reflection coefficient at the load. So that is ZL minus Z0. It is according to the formula ZL plus Z0 if load is real. In that case, we know ZL, Z0, ZL and Z0. So we will put the values and we will find, this is load, 50 divided by 150. From here we can get gamma load is 1/3. This is the reflection coefficient at this point, but our aim is to find at this point. So for that purpose, that is at the load, at the source side, we can say gamma in reflection coefficient in input side is equal to the at L dash. L dash is at lambda by 4. L dash is the distance from here to here. It is considered as L, and the length from here at this point is considered as L dash. So that is lambda by 4. So at lambda by 4, we will say at load times e to the power minus j2 beta L dash from this formula. So L load we know, reflection coefficient at load we know, and e to the power minus j2, the formula for beta is 2 pi by lambda. However, the length L dash is equal to the lambda by 4. So now this will be the reflection coefficient at a distance lambda by 4 from the load side. So we can say 1/3, lambda will be cancelled out, 4 will be cancelled out, e to the power minus j pi. And if we will further simplify, then we will find cos minus pi plus j sine minus pi, and from this we can say cos pi is equal to minus 1 plus 0. So the final value that we will have the reflection coefficient at this point, that is input side, is equal to the minus 1/3. So the final result will be minus 1/3. Now let us consider the load is complex. That is RL, RLC, LC, somewhat like that, not only a resistive load. So in that case, if the load is complex, then formula it will remain same as it is, ZL minus Z0 divided by ZL plus Z0 for reflection coefficient. However, ZL can be written as RL for RL load, RL plus JXL L minus Z naught, we can write like that, RL plus JXL plus Z naught. We can write at the place of ZL the exact load, real plus inductive load. So from here we can say RL minus Z naught plus JXL divided by RL plus Z naught plus JXL. And if we will try to find the magnitude of this, then we can say it will be square RL minus Z naught square plus XL square divided by RL plus Z naught square plus XL square. We can write like this, and as it is the complex one, so there will be phase as well, and that phase can be written as the tan inverse XL divided by this RL minus Z naught minus this formula tan inverse XL by RL plus Z naught. So this will be phase and this will be magnitude. So from here, if the load is complex, not real, in that case the reflection coefficient will be, load will be gamma load magnitude with phase J phi because of the complex nature of the load. Okay. Now if we wish to find at any particular length in between the length of the line, for example that is at length L dash from the load side, as we have done in previous case, so let us write reflection coefficient at any distance L dash from load. So in that case the reflection coefficient we will take from here. So L dash will be equal to the load, as we have done in previous case, e to the power minus j 2 beta L dash. If you remember, then the formula was this, and this we can place like that. So it will be load times e to the power j phi e to the power minus j 2 beta L dash, and after further simplification the magnitude of this with e to the power j phi minus 2 beta L dash. So it will be the reflection coefficient at any particular length L dash from the load side. So this is for complex load, when load is other than only resistive nature. So in that case this will be reflection coefficient. Okay, and this is the reflection coefficient at the load side. Due to lack of time, I am unable to cover the numerical problems at this stage. However, I will provide them to you through the tutorial sheet. So thank you very much. From the next time we will start the last unit, that is the application of the wave. Thank you.